This is my Lab 2 video, excess charge on an ordinary object. So to quickly go over this lab, we did several experiments with Scotch tape in order to display the interaction between charged objects. Then, using the data that we gathered there, we created a computational model to demonstrate the experiment. Unlike last time where we represented the tape as a point charge, this time it was treated as a uniform rod, where we broke it down into segments of equal length with equally distributed charge, and then calculated each segment's electric force separately, and then summed it all up. Now, there's a few fundamental principles necessary to understand this lab. First is Coulomb's law, that opposite forces attract and like repel. This also gives us the equations for both electric force and electric field. Then there's Newton's second law, force equals mass times acceleration. This tells us that if an object is not in motion, all forces acting on it are equal. Last of all, there's superposition, the idea that the net electric field at a location is determined by the sum of all individual electric fields on charged particles. To carry out this experiment, we created two charged U-tapes. These tapes repel each other, so using Coulomb's law, we know that they have the same charge. This experiment was set up by suspending tape B in midair and bringing tape A to the underside of tape B. Because they have like charge, they repel each other, and the electric fields from force A, from tape A, caused tape B to essentially float. The experimental data we gathered was that the length of the tape, the mass of the tape, and the distance between the two tapes from tape B was floating. From this, we were able to calculate the force of gravity on tape B. As you can see, I did a force diagram of tape B on the right, where we have in the y direction the electric force and the gravitational force. Now, these have to be equal since Newton's second law tells us that since the tape isn't moving, its acceleration is 0 and its forces are equal. So knowing that, we know that the electric force has to be equal to the gravitational force of 0.002 newtons. So this is the code for my model. First and most important is the observed constants. Here we have mass, charge on each of the tapes, distance the top tape floated, and charge of a proton, and gravitational force. The most important part of this code is in this while loop. Now the object of this model is to figure out the amount of charge necessary on one piece of tape to float the top tape above the bottom tape by the measured distance of 0.018 meters. Now, this while loop does just that using Newton's second law. It runs as long as the magnitude of the known gravitational force is greater than the magnitude of the calculated electrical force. Now, when this model runs the first time, the magnitude of the electrical force is going to be much smaller than the magnitude of the gravitational force. So what we're going to do is that each time this while loop runs, we increment the charge in order to get as close to that gravitational force as we possibly can. Now, when we run this program, the most important part of this code, we can see that we do get really close to that gravitational force. The object of this model is and we find that our charge is different than the one that we calculated with our other model, our model that treated the tape as a point charge. Here on this model, you can see that there's a lot of green arrows, and that represents the electric force on each individual segment of that piece of tape that we have broken up. Of the known gravitational force is greater than the arrow represents of the electric force on the tape, and the yellow arrow represents the gravitational force. So just some additional things about this lab. I want to go over the superposition a little bit more. Now, the green arrows, they represent those individual electrical forces, and by summing up all of those vectors, we get the white arrow. Now, the reason that the white arrow is only pointing in one direction and the green arrows are pointing in other directions is because all the green arrows x directions cancel each other out, and we're left with only a force in the y direction. Now, the model calculated magnitude of the charge on one piece of tape was 9.004 times 10 to the negative 9 coulombs, and we had some assumptions in this lab. We ignored air resistance on a moving object, and we assumed that each U-tape had about the same charge and that the charge was evenly distributed along the length of the tape. So in conclusion, to compare the point charge model and the line charge model, we see that the line charge model has an estimate of the tape's charge that's larger. It's 9.004 times 10 to the negative 9 coulombs as opposed to 8.404 times 10 to the negative 9 coulombs. This is expected, and we did expect these estimates to differ because the point charge model is oversimplified and the line charge model just requires more calculation. Because the line charge model requires more calculation, it's more accurate and it's more like the physical world. We're breaking it down into smaller components and calculating based on those components, so it's much more accurate.